Welcome to the next lecture in Math 1342, Elementary Statistics at Dallas College with Professor Bailey, specifically using the ALEKS system. Today we're looking at 8.1, Basic Principles of Hypothesis. We're going to define the null and alternate hypothesis, describe the reasoning used in hypothesis testing, state conclusions to hypothesis tests, and learn how to distinguish between type 1 and type 2 errors. We've described the statistical analysis as a four-step process whose steps are to formulate questions, collect data needed to answer those questions, describe the data, and then draw conclusions using appropriate methods. We now discuss how to perform hypothesis tests, which is one of the most commonly used methods for drawing conclusions about your data. So let's look at an example. Air pollution is a serious health problem in many cities. One form of air pollution is particulate matter, which refers to particles that can be trapped in the lungs. One study published in the Journal of Air and Waste Management reported that a mean amount of particulate material produced by cars and light trucks is 35 milligrams per mile of travel. A new engine is designed to reduce this level. There are two possibilities. Either the new design will reduce the level, or it will not. These possibilities are called the hypotheses. One hypothesis, which we call the null hypothesis, says that the new design will not reduce the level. The mean remains as mu equals 35. Okay. The null hypothesis is always stating that there is no change to whatever value you're looking at. In this case, we're looking at the mean, the average. Another hypothesis, which we call the alternative hypothesis, says that the new design will reduce the level so that the average, or mean, mu, is less than 35. Our alternative hypothesis is always the one that we're kind of trying to test out, and our null hypothesis is always the one that says it did not change. We denote the null hypothesis by a capital or uppercase letter H with a small zero at the base, a sub-zero, if you will. The null hypothesis, denoted by H sub 0, states that the parameter is equal to a specific value. For example, the last example, this was that the mean equals 35. The alternative hypothesis, denoted by H sub 1, states that the parameter differs from the values specified in the null hypothesis. And there are three types of alternative hypothesis. There's a left-tailed hypothesis, and this states that the parameter is less than the value from the null hypothesis. There's the right-tailed, and if you think of the normal curve, you can see this is that these values are greater than. So the right-tailed hypothesis states that the parameter is greater than the value from the null hypothesis. Again, from our last example, this would mean that the average, or mean, mu, is greater than 35. And then there's another hypothesis, not greater than, not less than, and this is the two-tailed hypothesis, that the parameter is just not equal to the value from the null hypothesis. And this, as you can see, although this notation is wrong, all of these notations are wrong, these should all state H sub 1. I just noticed that. That the hypothesis does not equal 35. So again, all of these are incorrect notations. These are alternative hypotheses, so they should be denoted by H sub 1. I'm sorry for that typographical error. See if you can state an appropriate null and alternative hypothesis for these three. Hit pause and try this. I'll go through the first one now, and then again, hit pause and try these. They're pretty straightforward, but it's good practice. We've got a couple screens of this. So in the first one, boxes of a certain kind of cereal are labeled as containing 20 ounces. An inspector thinks that the mean weight, the average weight, may be less than this. So remember, our null hypothesis is that it doesn't change. So our H sub 0 is that the mean, mu, equals 20. Our alternative hypothesis says less. So H sub 1 is that mu is less than 20. You can see here highlighted, these are the hypotheses. See if you can do these. They're very straightforward on your own before you continue forward. It should just take you less than 30 seconds. In the second example, the mean monthly rent for an apartment in a certain city was $800. A real estate agent believes that the mean rent is higher this year. So our null is the mean equals 800. Our alternative is that it's greater than, because he thinks the rents are higher. Scores on a standardized test have a mean of 70. Modifications are made, and an educator believes that the mean may have changed. Notice here we are not given a value greater than or less than. This is just saying they think it's changed. And so in this case, our null is still 70. It hasn't changed. And our alternative is that it will change. It doesn't give a direction that they think it's higher or lower, just that it'll be different. Again, 3 more. Try these. Last year, the mean amount spent by customers at a certain restaurant was $35. The owner believes that the mean may be higher. Null mean equals 35. Alternative mean is greater than 35. In a recent year, the mean weight of newborn boys in a certain country was 6.6 pounds. A doctor wants to know whether the mean weight of newborn girls differs from this. So our null is that the mean weight is 6.6, and our alternative is that the mean is different. It doesn't say greater or less than, just differs. Certain model of car can be ordered with either a large or small engine. The mean number of miles per gallon for cars with a small engine is 25.5. An automobile engineer thinks that the mean for cars with larger engines will be less than this. So our null hypothesis, the mean equals 25.5. And our alternative is the mean is less than 25.5. Okay. So why do we do these hypothesis tests? Why do we not just look at the values and then move forward? Well, the purpose of the hypothesis test is to determine how plausible the null hypothesis is. The idea behind a hypothesis test is similar to a criminal trial. At the beginning of the trial, the defendant is assumed to be innocent, and then the evidence is presented. If the evidence strongly indicates that the defendant is guilty, we abandon the assumption of innocence and conclude the defendant is guilty. In a hypothesis test, the null hypothesis is like the defendant in a criminal trial. At the start of a hypothesis test, we assume the null hypothesis is true. Then we look at the evidence, which comes from the data that we've collected in our survey or whatnot. If the data strongly indicates that the null hypothesis is false, we abandon our assumption that it is true and believe the alternative instead. This is referred to as rejecting the null. Okay, rejecting the null. We reject the null hypothesis when the data provides strong evidence against us, and this evidence comes in the form of a test statistic. When the difference between the test statistic and the value in the hypothesis, the null hypothesis, is sufficiently large, we reject the null hypothesis. Let's look at an example. Suppose an exam has been given to a large class and the instructor claims that the mean score on the exam is 80. This is the null hypothesis, mu equals 80, right? Now suppose that a sample of exam scores is selected and the sample mean is x bar. This again is the mean from a sample, equals 78. Here you can see it in a diagram of a normal curve. Because 78 is relatively close to 80, it's plausible that the null hypothesis is true. Imagine, however, that the sample mean had been 50, which you can see in this diagram at the bottom to the right. Because 50 is far from 80, we have a great distance here versus the other, it does not seem plausible that the population mean is actually 80. So in this case, we would reject the null. We see that the farther the test statistic is from the value specified by the null hypothesis, h sub naught, the less likely the difference is due to chance, and the less plausible the null hypothesis becomes. The question then is, how big should the difference be before we reject the null hypothesis? To answer this, we need methods that enable us to calculate how plausible the null hypothesis is. Hypothesis tests provide these methods, taking into account such as the size of the sample and the amount of the spread in the distribution. If the null hypothesis is rejected, the conclusion of the hypothesis test is straightforward. We conclude that the alternative hypothesis is true. So if we reject the null, what we're going to conclude is that the alternative hypothesis is true. If the null hypothesis is not rejected, there's not enough evidence to conclude that the alternative is true. And so while we don't say that we reject the alternative, we just say that there's not enough evidence to conclude that the alternative is true. So we either, if we reject the null, we conclude the alternative is true. If we don't reject the null, we still talk about this in terms of the alternative hypothesis, specifically that there's not enough evidence to conclude it is true. This is not saying the null hypothesis is true. What we're saying, the null hypothesis might be true. Hypothesis testing can be confusing because it's essentially a statistical method for evaluating the likelihood that a specific hypothesis is true, but it's not about proving it definitively. This is why we use all of that very careful language with our conclusions about confidence, and in this case with hypothesis testing. Hypothesis testing focuses on the probability of observing the data given a particular assumption, not the other way around. This can be difficult to grasp, especially for those without a strong statistical background. But remember that when we've done the normal curve, we've figured out probability. We've used z-scores to talk about the area under the curve, which represents either a proportion or a probability. So we're going to be focusing on the same thing we've looked at in a number of different ways earlier in the course. So again, when we have a hypothesis test, if we reject the null, our conclusion is the alternative is true. If we don't reject the null, we don't talk about the null, we just talk about the alternative still. Both of our conclusions are about the alternative, and when we cannot reject the null, we say there's not enough evidence to believe the alternative is true. So again, all of our conclusions are about our alternative hypothesis. A box of cereal are labeled as containing 20 ounces. An inspector thinks the mean weight may be less than this, so he performs a test, with the null hypothesis being the mean equals 20, and the alternative hypothesis being that the mean is less than 20. So if he rejects the null, then we support the alternative. We conclude that the mean weight of the cereal is less than 20 ounces. Again, what we're doing here, if we reject the null, no matter what we do, we're talking about the alternative. Since we've rejected the null, we're concluding the alternative is true. If we don't reject the null, again, notice that our conclusion is not about the null, it's about the alternative. And here we just state there's not enough evidence to conclude that the mean weight of cereal boxes is less than 20 ounces. When a hypothesis test is conducted and a decision is made, there is a possibility that it is a wrong decision. There are two ways in which a wrong decision may occur in hypothesis testing. If the null hypothesis is true and we mistakenly reject it, a type 1 error occurs when we reject the null when it's actually true. Okay. On this table down here, you can see the decision. This is like what is real. The null is true, the null is false. So if the null is true but we reject it, we've made a type 1 error. If the null is true and we fail to reject it, well, this is a correct decision. If the null is false but we mistakenly decide not to reject it, this is a type 2 error when we don't reject the null when it's actually false. So here the null is false, but we fail to reject it, and this is called a type 2 error. So type 1 is when the null is true, And type 2 is when the null is false, and we do the opposite. In general, a type 1 error, when the null is true and we reject it, is more serious than a type 2 error. This is because a type 1 error results in a false conclusion. Remember, when the null is false and we claim it, we say that we don't have enough evidence. But if the null is true and we reject it, we're saying the alternative is true. And so that's why this is more serious. Ideally, we'd like to minimize the probability of both of those errors. Unfortunately, with a fixed sample size, decreasing the probability of one type increases the probability of the other. So you can think of it kind of like a seesaw. If we reduce the error on type 1, the type error goes up, and vice versa. The hypothesis tests are often designed so that the probability of a type 1 error will be acceptably small, often 0.05 or 0.01. Now, these are probabilities, so this is like 5% or 1%, right? And this value is called the significance level of the test. We've been looking at some confidence intervals, and this is very similar in thought to that, right? We are 95% confident. Here we have 5% left in the tail, or etc. Okay? So let's look at this. The dean of a business school wants to determine whether the mean starting salary of graduates of her school is greater than 50,000. She will perform a hypothesis test with the following null and alternate hypotheses. The null is that the mean is 50,000 and the alternative is greater than 50,000. If the true mean is 50,000 and the dean rejects the null, what do we have here? Do we have a type 1, type 2, or a correct decision? Well, if the mean is 50,000, that was what our alternate hypothesis states, but the dean rejected it. So this is an error, and because the mean is true and we rejected it, this is a type 1 error. And you can see that here. The null is true, but it's rejected. It's a type 1 error. The true mean is 55,000, and the dean rejects the H sub naught. Okay, the mean is not. It should be rejected, and our hypothesis is that it's greater than, and this value is greater than. So this would be a correct decision. Here we would be affirming that the mean is greater than $50,000. If the null is false, I'm sorry, I'm at the wrong place. The true mean is 55 and the dean does not reject it. Okay, so here the mean is not 50,000, so the null is false, but the dean does not reject the null, and this would be a type 2 error. When the mean is false and you don't reject, you get a type 2 error. And there's some more problems here. I suggest you try these. These are pretty straightforward, and it's just good practice. Think of it like drilling. Like if you were going out for the basketball team, your coach would have the whole team practicing free throws at some point, and you would do this repeatedly. This is not that many. It doesn't take long. So just hit pause. Try these 3. It's pretty straightforward. Okay, I'm not going to explain these. You should be able to, again, you can hit pause and think them through, etc. Again, we talked about writing the null and alternative hypotheses, how to determine whether a hypothesis test is left-tailed, right-tailed, or two-tailed, how to state that conclusion. Remember, we always state it in regards to the alternative hypothesis, and how to distinguish between the type 1 and type 2 errors and correct decisions.